Welcome to Chapter 9, where we're going to talk about solids and fluids. So my picture here has a picture of a solid, liquid, and gas. Happen to at least look like they're ice, water, and steam. But we're going to forego talking about gas, and we're just going to talk about solids and liquids, but in a special way, not just their characteristics, which actually gets discussed a little bit in chapters 10 and 11, which we don't do in this class. So we're going to kind of pick and choose the topics from chapter 9. So we're going to talk about stress, strain, and elastic moduli in regard to solids. Then when we talk about fluids, we're going to talk about pressure, the kind of pressure that acts on fluids, and that also then is intertwined with Pascal's principle. And then we're going to talk about buoyancy and Archimedes' principle, which has to do with floating and displacement of liquid when a solid is floating. And we'll talk a little bit about surface tension and viscosity, but we'll skip over the fluid dynamics, Bernoulli's equation, and Poiseuille's law. I forgot to take out my one little slide thing. All right, so solids and elastic moduli. So the first thing that's important to stress here is that these equations for stress and then subsequently strain and Young's modulus pertain only to solids. So we can apply a force, as we can see here in our diagram, where we have either here, right, we have, I lost my pen, there it is. So here, this is a tensile stress. So this is kind of like we're pulling on both ends. Right? So we're stretching. So we could call it pulling, we could call it stretching. But then we can also have our forces inward, and so this is a compression stress. So we can think about this in terms of springs, where we either stretch to spring or we compress to spring, and then we talked about the results of that and spring constants, etc. So our key equation here when we talk about stress, it is the force per unit area. This is the area, if we're talking about, say, these rods, this would be the area of the end of our rod, right, opposed to the length of our rod. And so we can stretch it, right, so that it actually gets slightly longer due to physical forces acting, right? Or if we talk about compressional stress, we can actually make it shorter by having forces that are inward. Right? And we'll talk a little bit more about that. But first, it makes sense to do an example so we can see exactly how this works. So suppose you use the tip of one finger to support a 5 kilogram object. And your finger has a diameter of 2 centimeters, at least that's where, right, this object is covering, right? And we want to know what is the stress on your finger. So I'm going to draw, so that'll be scary. So here's my finger. Here, I have a little fingernail. Hey, that's pretty good for me. Now, it should really be up. Here, this is at my fingernail. Right? And here is my object. And it's some kind of cylinder because they've given us, right, whoops, a diameter. Oops. There we go, diameter. And it happens to be in centimeters. Right? But stress is usually in newtons per square meter. So we're going to change our units a little bit. So here is, right, our object sitting on our finger, right? There is a force acting on our finger, that happens to be the weight, right? And then our finger has a force back on our object, which happens to be the normal force, right? So here, the force acting on our finger, because that's what we're interested in, right? So the force acting on my finger is the weight of my object. So that's 5 kilograms times little g, 9.80 meters per second squared. I think that should be about 49, but I'll make sure. 49 newtons. Yes, it is exactly 49 newtons. So this is 49 newtons is the force acting on my finger. Now I need the cross-sectional area. And so it's a circle, right, because it's a cylinder. And so we're only interested in that bottom area, so pi r squared. But we want to find it in square meters, so 2 centimeters. Right? So our diameter, right, is 2 centimeters. But centi is the same as 10 to the minus 2. That's why we like, right, SI units, metric, because it makes our life easier. So here we have pi times r, so that means that I would just divide each of these by 2. So I have 1 times 10 to the minus 2 meters. And then I'm going to square all that. And I will calculate it because that always makes students happy. So I have, whoops, helps if I plug in my numbers right. 1 times 10 to the minus 2. And then that's times pi. And that's 0.03141, right? It's basically 0.001 times pi. And so we'll just call this 0.031 square meters. And now we're ready to calculate our stress. That's going to be our 49 newtons divided by our cross-sectional area. And so we can see that it's actually, right, going to be a somewhat large number because we're dividing 49 by what's really a relatively small number. And when I calculate this, I get a big number, which we'll then write in scientific notation. So 1,560 newtons per square meter. Right? 2 significant figures, right? So we'll write it as 1.6 times 10 to the 2 newtons per square meter. And so that is the stress, right, that is acting on our finger, right? And we could probably see, right, it actually depress our finger a little bit, right, with that force that's acting from our 5 kilogram mass. When we talk about solids, we also talk about elastic moduli. So stress results in a change in the shape of the solid, right? And so we have already looked at that picture when we talked about that, right here, where we talked about delta L and L initial, which is LO. And so here we just see that as a measure of strain. So if we know the change in length, right, which is final minus initial, just like all of our change-ins, and we divide it by the original length of our solid, then we can calculate the strain. Obviously, strain has no units, right, because our length, our change in length is going to be, say, in meters. Whoops, stop. In meters, and then our original length might be in meters. If our change in length is in centimeters, right, and this is in meters, then we obviously have to change our units, but strain has no units. Strain is related to the stress. We could see that in our picture here 2 slides ago. And so now we can combine that strain calculation and the stress calculation to figure out our elastic modulus, which is, it looks like a Y, but it's not really a Y, it's a Greek letter. I think it's epsilon. So here we have newtons over square meters over no units, so our elastic modulus is also going to be in newtons per square meter. This reflects the stress over the strain. So here we have our ability to calculate just this very thing, strain. So we have a rod that starts off, right, it's initially 5 meters long. And then it's stretched by some force that we don't know, right? So we can't figure out the stress, only the strain. And it's stretched an amount, right, that's delta L, 0.10 meters. And we want to know the strain on the rod, and so we're just going to use the above equation so that my strain is the change in length over the original length. So we can literally kind of think of it as a percentage of the change, conceptually. So we have 0.1 divided by 5, right? So 0.020, right? 0.020. We'll have two significant figures, right? And again, my meters cancel, so it has no units. Right? If we thought of it conceptually, this would be a change in length of 2%. Right? So it's always a kind of a natural way of thinking about it, although strain is usually presented just like this. When we combine our stress and a strain, we can have a curve. And when I worked in industry, we did something very much like this, where we tested different solid materials that we manufactured, right, where we literally put them in a machine that stretched it until it broke. And so that's what we were interested in, so we could figure out the elastic behavior of that material. So we can physically think about, right, this pulling, right, and our stress and our strain. So here's stress versus strain, right? And we have this nice linear elastic behavior, at least at first, where our stress is proportional to our strain, but then we start reaching our elastic limit, so we actually start to deform our material, right? And so it becomes non-linear. And then this is always a sign, once you start curving off the linear path, that we're actually going to soon break this material, this object, right? Because we've reached or surpassed the elastic limit. So in other words, we're still applying a force, right? It just can't stretch anymore without breaking. Right? You can, for all of our exercise science and future physical therapists, this is like if say somebody tore a muscle, right? We would see this same kind of thing. So we could stretch an ACL, but we wouldn't necessarily get to the point where we could deform it and it not break, or we can, right, tear it even if it doesn't tear completely. So this is that same exact application. So here, this is just a table in Chapter 9, Table 9.1, where we can just look up the Young's modulus, shear modulus, and bulk modulus of specific materials. You notice that we have here in the solid realm, we have aluminum and bone, right? So, and bone, we can actually, right, compress or stretch. Fun times. And but when we do that, right, they have a different Young's modulus. Isn't that interesting? Look how much bigger the compression is than the tension. Or no, sorry, it's 10 to the 9th. It's 10 to the 10th. This tension is the biggest one. Oh, that makes more sense. Here's brass, right? Copper, glass, right? Iron, right? So we can see this comparison. We just have to be careful about, right, our factor of 10. And then we can actually look at not Young's modulus or shear modulus, because those are one-dimensional, but we can look at bulk modulus, right, which is symbolized with a B. We can look at bulk modulus if we look at liquids, right? We can only look at bulk modulus in regard to liquids, because liquids can only be three-dimensional, right? Solids can be one-dimensional. We can look at one dimension, we can look at 2 dimensions, or we can look at 3 dimensions. So this is why we have a bulk modulus that only has to do with liquids, but we have Young's modulus, right, change in length, basically shear modulus and bulk modulus, right, across all of our solids listed here. So if we then move to fluids, right, we can still have something that is force per unit area. Remember, for solids, right, this was Young's modulus, or sorry, this was the stress, right, and we said stress was equal to the force over the cross-sectional area. Right. Here, because it's not a solid, so this is only for solids, we call it stress. For liquids or fluids, right, we have the same equation, but this is a measure of pressure, right? Because liquids can more easily deform, so we have, right, a different terminology to describe something that's a little different happening. So here we have the force, right, acting at an angle to the surface, right, and then we can just have force perpendicular over the cross-sectional area, right, or just the x component that's going into our material, our fluid. Doesn't mean that our fluid can't be in a container like a piston of some, well, those are usually gases, but right, where we're compressing or, right, expanding our liquid in some kind of container. So the unit of pressure, there are actually multiple units of pressure, but when we talk about the pressure in fluids, we talk about it in terms of Pascal. The reason for this is because our pressure, right, was force per unit area, cross-sectional area, and so that makes the Pascal, right, the natural measure of pressure in fluids. If you've taken especially chemistry before, right, then you've seen some other measures of pressure, right? So we have atmospheric pressure, right? And then we also have millimeters of mercury as another measure of pressure, for instance, right? So, but especially atmospheres, this is most often used relative to gas. So we happen to live in one atmosphere, right? That's the pressure that exists basically on Earth. We can also look at density, right? And so density, right, is also, right, we can talk about density of a solid, but we can talk about density of a fluid as well. Either way, the density is the mass per unit volume, and we actually talked about this a little bit way back in chapter 1. And so, of course, we have another table, right? And this table is for fluids. And here, right, we have all different kinds of densities. Oh, sorry, it says fluids, but it's not. It's common substance. It's got solids and liquids, sorry. Right, so here are densities of solids. Here are our density of liquids, and gases also have density. So you notice that if we talk about density of ice, right, which is frozen water, it is different than the density of water. Not by a ton, right? And the ice is, right, got a smaller density, a little bit. And then here is the density of water vapor. It's completely different, right? And so these are just the interesting things about, right, density, if we even have the same substance, but it's in a different state. So when we talk about pressure in a fluid, right, we can actually put an object. It could be a solid object. Here we have a solid object. We stick it in, right, a beaker of some kind of fluid. And so now we can calculate the new pressure, and where we say, well, this block that we have in here, right, it's got a weight mg that's acting downward. It's got a height, right? So the height of our object and its weight come into play here. But really, it's not so much the mass, right, or weight, mg, right? Here we can look at this in terms of cross-sectional area, right, and our weight, and so we end up with this expression. This is a P for pressure. This is rho for density. This is G as in 9.80 meters per second squared, and this is H, right, the actual physical height of our object, right? And here's that A that's in our equation here, right? So we've worked through all of these other aspects to come up with this equation right here. So we can find the pressure in the fluid if we know the pressure initially, right? And then the density of the object that we put in the fact that we're on Earth and then the literal height of that object. Pascal's principle is when we now apply pressure, right, to an enclosed fluid. So again, it could be in some kind of box where we can compress the sides, right? We can compress the top, we can compress all four vertical sides, we can press the bottom, right? And when we do this, our pressure is applied or transmitted, right, throughout the entire fluid, right? And then that in turn pushes also on the wall. You can think of it as if you put a liquid in a container and then took away the container, right? The liquid doesn't stay in that form anymore. So since the pressure is constant, a small force acting over a small area can become a very large force acting over a large area. And here we can look at the hydraulic force, which is a ratio of our areas, right? So here, if we come over here, oh, I thought it was on this picture, but I guess not labeled. So we can see how our area, right, affects our hydraulic force. It could literally be like a multiplier. So here we have hydraulic lift in a garage, and it has two pistons, right? A small one, and our small one, right here, oops, is right here. This is our small one. Here is the force applied here. Here is the cross-sectional area of our, right, our small piston. So this is the small, right? And by pushing this down, right, our fluid actually acts onto our much larger piston. We can lift our car, right? And here we have the cross-sectional area, which is the area, cross-sectional area of our larger, right, part of our piston, right, which is where our compression force acts, right, from the small piston to the larger piston. And we can also, right, push here. So we have our small piston has a cross-sectional area of 4 square centimeters. So that is our AI. And our other area has, right, it's much larger, and it's 250 square centimeters. So when you see square centimeters, you might think, uh-oh, I have to convert these to meters or square meters. But it doesn't matter, because what we really have here is a ratio, right? So it doesn't have any units. The only requirement is that these two have to be the same units. Doesn't matter what units they are. And so we can calculate our ratio of, right, our larger piston's cross-sectional area to our smaller. And so that gives us 250 square centimeters divided by 4 square centimeters. Again, our square centimeters cancel. So we have 250 divided by 4, which I should know off the top of my head, but apparently I haven't had enough coffee yet. So no, I should know that. That's 62.5. No units, right? Because my units cancel this. So what this really means is the force acting on my hydraulic lift on our car here, right? That force is going to be 62.5 times bigger than the force applied here at our smaller piston. So now we're ready to figure out what exactly the force is. So, right, this lift is designed to raise a 3,000 kilogram car, and we want to know what minimum force must be applied to the small piston in order to do this. So here we're actually looking to find Fi. we know what the minimum force is over here for FO, right? The minimum force is just enough to balance out the weight downward of my car. So FO minimum is simply mg. So I can figure out then the weight of my car, so 3,000 kilograms times 9.8, and that gives me, and I'll ignore significant figures for right now, so that gives me 29,400 newtons. So I have here, right, I can take FO, divide it by my ratio of my two areas, so I'm going to divide by 62.5. And that's going to give me, right, the force I need to apply to my small piston. So that's 29,400 newtons divided by 62.5. And so what force do I have to apply? 470 newtons. So if I apply 470 newtons here at my small piston, it will actually result here with a much larger force, a force minimum of 29,400 newtons. And so that is how hydraulic lift in a garage works. So we've talked about fluids and pressure and Pascal's principle. So now we can look at how do we measure this pressure? There are multiple ways. One is that we can have gas under pressure, right? And this includes some of the breathing measurements that doctors make, where we blow air in, right? And we see how our liquid changes height, right? And this happens to be a measure of absolute pressure. If you use one of these typical tire pressure gauges, even if it doesn't look like this, if it's one of the ones with the circle, basically, it's a gauge, doesn't matter, right? Tire pressure gauges measure gauge pressure. So they actually measure the difference in pressure between what's inside your tire and what's outside your tire. So what's outside your tire? About 1 atmosphere, which is 14.7 pounds per square inch. Right, so that's a handy thing. So if you measure your tire pressure with the tire pressure gauge and it says it's 30 psi, pounds per square inch, right, we actually have to add 14.7 to that. So it's actually 44.7 pounds per square inch. That's the actual measurement in your tire. But again, right, these kind of pressure gauges measure the pressure difference rather than the absolute pressure. And then finally we have barometric pressure. Right, so we talk about millimeters of mercury, right? This is actually, right, how we end up measuring barometric pressure, right? So from a barometer. And so it has to do with the density of mercury, right? The fact that we're on Earth, and then the height of that mercury, typically in millimeters when we report it. So here we have a problem. Right? We want to know the pressure, right, exerted by a person's lungs can be measured by having the person blow as hard as possible into one side of a manometer, right? What's a manometer? It's basically, right, this right here, right? This is basically a manometer. Right, and so the person, oh, sorry, no, I don't think it should be that. Is that though? Can be measured by having the person blow as hard as possible into one side of a manometer. For a person blowing into one side of an open tube manometer, so that's the difference, right, produces an 80 centimeter difference between the heights of the columns of water in the manometer arms. What is the gauge pressure of the lungs? So here, because it's open, whoops, wrong way. Because it's open, we just have, right, because it's open, we don't have, oops, we don't have this PA, right? It's open, so it's just open to, so there's not a push down here, and so we end up with just PGH, which happens to be, right, similar to the barometric pressure idea. So here, right, where I'm up 80 centimeter difference. So that's the change in our height. So it would be something like this. So our height equals 80 centimeters. Okay. And we want to know what is the gauge pressure of the lungs. Gauge pressure, right, is going to be our measurement here. Right, so we can say, oh, well, we're going to measure this pressure, right, is going to be the density of water. So here's our density of water. Oh, and I forgot to look, so I have to flash back, but I'm pretty sure that's in density. There we go, in kilograms per cubic meter, right? So that's important, that that's our density is in kilograms per cubic meter. So this is in kilograms per cubic meter. Why is that important? Because we have to worry about our units here, right? So 80 centimeters, centi, is the same as 10 to the minus 2, and so our height change is 0.80 meters. So I'm just putting everything in SI units. So my PA is going to be the density, 1 times 10 to the third. Again, that's kilogram meters per cubic meter, sorry. Then times G, which is our usual G, 9.80 meters per second squared. And then times our height, which has to be in meters also. So here I have cubic meters. One of these cancels here, this one of them cancels this one, and so I end up with just kilogram, right? So I have kilograms per meter second squared. But here, right, we remember that pressure, that pressure was basically the force per unit area. And so force in newtons is a kilogram meter per second squared. And our area, right, is in square meters. And so here we can see, we can do some do-si-doing, right, and say, well, you know what? I only want to cancel one of these, and I'm going to keep this meter, and I'm going to keep this, right, meter squared, only so that I can then look at it and go, oh, my units are going to be kilogram meters per second squared per meter squared, which means that my units are newtons per square meter, which means that my unit is a Pascal. So I just did a little quick unit analysis, right, to make sure, for one thing, that everything is all copacetic. And so now I'm ready to stick my numbers in here. So I have 1 times 10 to the third, so that's just 1,000, times 9.8 times 0.8, right? And we already know where our units are, and so this gives me, right, 7,840. Right? And we're just going to label it as pascals. So that is, right, the pressure of the lungs, right? And here's just some other little manometer pictures that might look a little more familiar, where you have the patient blow in here and they make the little plastic huya go up, right? And there's measurements here. This is just that same height, right? So it allows you to figure out basically this same idea, right? So see if they have problems and with their lung, right? Their ability to blow out, right? So like a pulmonary kind of disease. So, and then here, right, we have just another version where, I think you can see it, but there's like also a little ball in here where it moves as well. So it's the same general idea. So fluids, we've talked about pressure and Pascal's principle. We already alluded to the fact that when we talk about gases especially, or the world we live in, we talk about atmospheric pressure, which is 1 atmosphere, right? And 1 atmosphere is 101 kilopascals. or if we're thinking about it in measures of mercury, millimeters of mercury, that's 760 millimeters of mercury. Right? So the pressure unit corresponding to 1 millimeter of mercury is called the torr. So 760 torr is the same as 1 atmosphere. So we just have some different units when we talk about pressure. So barometric pressure, I alluded to this before, has to do with the fact that we use a mercury column barometer. This brings us then to the idea of buoyancy and Archimedes' principle. So say we have a solid, right, and we put it in some kind of fluid, right, and it becomes immersed, maybe wholly, maybe it sinks to the bottom, right, or partially, right, it's floating and, right, only part of it is visible above the fluid line, right, you can think about like an iceberg, right. If this happens and we've put this body in this fluid, right, and then we say that it's experiencing a buoyant force, and that buoyant force is equal in magnitude to the weight of the fluid that is displaced. So, for instance, if we have a 2 cubic meter cube and we put it in water, right, it's going to displace how much water? 2 cubic millimeters, because it's going to displace the entire volume of our cube that, say, is metal, right? The metal cube's going to float to the bottom, so all of the water is, right, displaced is the same as the amount of water that is, right, displaced by the volume of our cylinder. Oh, here, I'm going to need to make sure that my buoyancy, hold on, I got to find my, oops, that's not what I want to do. I have to pause for a minute and make sure that alright, so here it is. It took a little while to come up. So here I have a ball, right, and I can pump my handle, right, so I can put gas in here. It's a heavy species, right, just means, right, basically it's a dense gas. And so here is my object, and it's just kind of floating above, right? And we can see how the temperature is changing. And then now, right, oh, I can compress it, and I can see how my pressure changes, right? So this is a little bit like some of the things we've been doing. Where is it? So this is the same idea. So now I just have it slightly different. It's just a hollow sphere, so it's just a different object. And so it's the same heavy species, and but it's hollow, right? And so we can see that it's interacting with our gas, and how it's floating is a little different than what we saw over here. Here I've added some pressure, so we can add some pressure here as well and see what happens. Come on, little guy. We also have a much smaller balloon. We can see that it's acting a little differently, and then I can compress it. So what's happening, and why is it that this balloon is acting differently than our much larger hot air balloon or our rigid hollow sphere, right? Balloons can at least be a little squishy. So this has to do with, at least partly, right, this idea of, right, the displaced volume of fluid or gas in this case, right? that's displaced. So we can figure out our buoyant force, right, is going to be m, right, the mass, right, of the fluid that's displaced times g. We can then replace, right, our mass of our fluid with the density of our fluid times the volume displaced of the fluid. And so in this way we can calculate the buoyant force that's acting on the object. So the object's density will tell you whether it will sink or float in a particular fluid. So this is where we can say, well, you know what, right? If we had that very small balloon, right, the actual material of the balloon, right, is a much larger percentage of, right, what's contained. So the volume is very different, right? If I have a big balloon, then I have a lot more air. Air is lighter, so we can see that this is why the density, right, is so important, right, along with the displaced volume of the fluid. So let's do a problem. So here we have an object has a weight of 8 newtons in air, right? So we start off, right, our object has a weight, so mg is 8 newtons. But it apparently weighs only 4 newtons when it's completely submerged in water. What is the density of the object? So here are a couple of things that we have to first consider, right? An object will float in a fluid if the average density, that's important, of the object is less than the density of the fluid. So this is a case where, right, we could think of, right, something, a piece of paper, right, that's floating on water. Right? Or we can have an object sink in a fluid if the average density of the object is greater than the density of the fluid. Right? Or an object will be in equilibrium at some submerged depth in a fluid, right, if the average density of the object and the density of the fluid are equal. Right? So we have a different thing going on, right? So here, this is, right, our actual weight. Here, right, when we say that this is 4 newtons, we can think of our object, right? It has a downward force of 8 newtons that is its weight, right? But it feels like when we add the buoyant force, right, we end up with 4 newtons. So we could literally say then that the net force, right, is 8 newtons minus the 4 newtons of the buoyant force. And so this 4 newtons here, that's the net force. That's what the apparent weight is. And so this is the buoyant force, just a different way of looking at it, right, than this calculation here. So the buoyant force is 4 newtons. It's supporting half of the weight of our object that we've put in, that's put in our fluid. So now, right, we want to find the density of the object. So we have, right, where's my little, oh, there it is. So we know that the buoyant force is 4 newtons. So I'm going to break my rule of not doing algebra first. Right? And, right, then we have our RO, right, that is going to be the density, right, of, oh, here it is. I was saying, didn't I have it here? Yes. Right, the object, so this is this, right, and then this is the fluid. Say, I thought I had it written somewhere. So our fluid is water, right, and we'll assume that it's 4 degrees and that our water is, and remember that this is in kilograms per cubic meter, because we love units. So we know that this is our row of our fluid. So we know this is 1 times 10 to the third kilogram per cubic meter. We want to find is the density rho, and here this is the weight of my object. So the actual weight of my object is 8 newtons. And so we can see that just by looking at this, the density of our object must be, right, twice as big as the density of water. How do I know that? And this is why I wrote it this way. Because if 4 newtons is equal to this number times 8, then this ratio has to equal a half. And so that tells me, without having to do more algebra, just conceptually, then that the density of my object must be twice the density of my fluid. And so that means it's 2 times 10 to the third kilograms per cubic meter. And in this particular chart, right, we don't see anything that has that density, and that's because, right, these are all liquids, and what we really have here is a solid. Right? We could look up density of a solid, but I think that's a number of slides back, and we could figure out what this object, what material it might be made out of, assuming that the object is, right, a solid piece of whatever. So the average density is what matters. So coming back to our balloon, right, the average density over our small balloon was larger, right, than the average density of our larger balloon. Right, so this is how a boat made of steel can float, because its interior is mostly air. Right? So, and an object's density can be changed. Submarines fill tanks with water to submerge, right? And then they, in turn, dump that out, right, so that it fills with air in order to rise. So that's how it can do both things, float and sink. Finally, we can talk about surface tension, which happens in liquids. This is how bugs can basically, right, walk on water, like little water bugs. Viscosity, so this is a lot of times if you ever had to buy oil for your car, right, there's different weights of oil, and this has a lot to do with viscosity, right, basically thickness, right, so maple syrup is much more viscous than water, right, and then Poiseuille's law, right? So all real fluids have some kind of viscosity, can't have zero, and that viscosity causes drag, right, as far as the movement of that fluid. And so these are just pictures that give us an example of that kind of drag, right, which also has something to do with surface tension. So, I'm going to have to pause again because it seems like it takes me forever for these things to pop up, and you don't want to wait for that. All right, so here we can see flow. So we have a flow rate of 5,000 liters per second, and we can come in and we can actually measure our speed at different points. And then we can change our fluid density, right? So right now it's water, but what happens if we make it more viscous? So we get to something that's more like honey. Well, now we can look at adding some friction so that it's more realistic. So we have our honey, right? And you notice here our pressure, that's 1 atmosphere, right? Basically 101 kilopascals. So we have nothing particularly exciting going on there outside. But if I come inside, right, I have a different pressure. And if we look at the pressure here, right, it's 139.7 kilopascals. But farther along, right, where the speed is actually going a little faster, the pressure is less. How about if I change my fluid density again, go back down to water, I still see that difference. Why? Because I've made this more real by adding friction into my system. I can have a much smaller fluid density, and look how different my pressure is now. So over here it's 120.3 kilopascals. If I increase my density, it goes up to 128.7 kilopascals. If I make it even more dense, right, 139.9 kilopascals. So we can see this relationship. If I change my flow rate so that it's slower, I can see how my pressure changes. Right? And isn't it interesting that as I make my flow rate smaller, my pressure actually goes up. Make my flow rate small or larger, and my pressure goes down. Right? But my speed, right, is faster. So this is basically what I wanted to show you as far as that kind of relationship, right, which ties right into what we are talking about here when we talk about liquid flow and viscosities, right? So here we have our fluid, right, and then we have our viscosity, right? The higher the fluid's viscosity, the more it resists flow, right? So it's harder to make it move. It has more resistance, and that's that viscosity. So we can, thinking about that, we can pop back into our simulation here, where we have smaller density, right? We see the pressure changes. And then we can reset it all, right? And then just do the same thing. Oh. And this is just the normal flow rate. So we'll come back over here. And that is the end of chapter 9, because we took out some of our things like Bernoulli, a little more complex. So decided that there was plenty in this particular chapter to fill everybody's brain. So these are the kinds of problems that we will look at as far as the homework for chapter 9.